To explore the initial rate method, we are going to look at the iodine clock reaction, where acidified hydrogen peroxide reacts to a solution containing potassium iodide, sodium thiosulfate, and starch. When carrying out initial rate experiments, it's always good to know what change you're expecting. Here, we're expecting a change from a colourless solution to one that is blue/black. I'm just going to pop my goggles on before I start the experiment. Wait for it. As you can see, our solution has changed from colourless to a blue-black colour. I am now going to perform an experiment where I change the concentration of hydrogen peroxide and measure how long it takes for the reaction to occur at each concentration. We're going to use 5 different concentrations of hydrogen peroxide. As such, I will need 5 conical flasks, which I will label A, B, C, D and E. I'm now going to prepare our reaction. To start with, I will add a solution containing potassium iodide and sodium thiosulfate to each conical flask. I'm going to use a 20 cm cube pipette for this, but first I need to rinse it out. On the bulb pipette, there is a line just above the bulb. This is 20 centimeters cubed exactly, and this is the line we are aiming for. As you can see, I'm slightly over, so I'm going to release a little pressure now, and there we go. When dispensing the liquid, touch the pipette to the conical flask to make sure the final drops end up in your flask. I am now going to add 2 centimeters cubed of 2 grams per 100 centimeter cubed solution of starch to each of our conical flasks. To do this, I'm going to use a pipette. Finally, I'm going to measure out 10 centimeters cubed of 1.0 mole per decimeter cubed sulfuric acid into beakers using a burette. It's important to make sure we clean our burettes using the same solution as we will be using in the burette. So I'm going to clean it with 1 mole per decimeter cubed sulfuric acid. Make sure the tap of your burette is closed. To clean, I slowly rotate the burette, angling it upwards each time in order to make sure that the liquid goes all the way down the burette. I can then open the tap and empty this into the waste beaker. You are now ready to fill your burette. Don't forget to make sure the tap is closed before you fill your burette. Luckily, my wonderful technician has already pre-cleaned and filled my burette with sulfuric acid for me. I'm going to measure 10 centimeters cubed now into each beaker. Again, I will be at eye level to make sure I put exactly 10 centimeters cubed into each one. As we get closer to our 10 centimeter mark, I close the tap of the burette slightly. This slows the rate of flow and therefore allows me to be incredibly accurate with my measurements. Now to prepare the hydrogen peroxide. You may have noticed that bottles of hydrogen peroxide are often labelled as 5 vol or 20 vol. This is because the concentration of hydrogen peroxide is given in volumes rather than moles per decimeter cubed. The volume refers to the volume of oxygen gas produced when hydrogen peroxide decomposes to produce oxygen and water. We can calculate the concentration of hydrogen peroxide using the balanced equation and the fact that 1 mole of gas occupies a volume of 24 decimeters cubed at standard temperature and pressure. I will now measure out our hydrogen peroxide. I'm going to measure out 30 centimeters cubed of 20 vol hydrogen peroxide. I have labelled my measuring cylinder to avoid confusion. My technician has pre-prepared other concentrations of hydrogen peroxide by adding 25, 20, 15 and 10 centimeters cubed of hydrogen peroxide to a measuring cylinder and then making each of them up to 30 centimeters cubed using distilled water. We are now ready to start our reactions. However, before we begin, let's think about the chemistry. The dramatic colour change we see is due to iodine reacting with starch. Hydrogen peroxide oxidises the iodide ions to form iodine. However, we don't see this straight away. This is because a second reaction is also occurring. As soon as iodine is formed, it reacts with thiosulfate ions to form tetrathionate ions in a second, faster reaction. Effectively, the iodide ions are recycled. Once all the thiosulfate is used up, free iodine remains in solution and can react with the starch, thus forming our blue-black complex. So now I need to borrow some hands to help me get this started.
Okay, 3, 2, 1, pour.
Don't forget to start your stopwatch as soon as you add your solution to your conical flask.
3, 2, 1, pour.
Don't forget to record all of your results in a table. I now need to repeat the whole experiment multiple times to get more data and ensure my results are reliable. You can see the results of my additional experiments in the table. As my reactions are now finished, I need to dispose of the reaction mixture. The reaction mixture contains iodine, which can be harmful to aquatic life. As such, I cannot pour it directly down the sink. I need to dispose of it in the correct method, which in this case is to pour it into a beaker containing sodium carbonate solution. The sodium carbonate solution reduces the iodine to iodide ions. This can now be safely disposed of by a technician.